So today I'm going to present in-memory key value store migration with NetMigrate. So basically, what is it? It's hybrid migration algorithm. It uses for key value stores, improving the query throughput at some level, and it applies on programmable switch. So what we already have, what migration type? So we have stop and copy. Basically, you're having a client sending a request to some proxy server, and they're taking data from your database source. Then you're stopping all requests from the client, copying all your database to the new destination, and redirecting your request to this destination database, and queuing previous one. If it's source-based, you're sending all requests to the data source and copying all dirty data to the new database destination. And the new data that's coming in time, it's stored in logs. Then you queuing the source database, copying the logs to the destination, and reproducing them. Afterward, you're redirecting all your requests to this database destination and queuing all old database. So in destination version of it, so basically what you're doing, you're sending all requests to the destination database. At the same time, you're copying all data to this destination. If the client couldn't find required data, it will just wait. And at this time, destination will try to pull this data from the source. How hybrid migration works. So basically, all your read requests will be split to both database source and destination, and you will get the most recent one. And your write request goes only to the destination. And during that time, you're copying everything from the source. So NetMigrate itself is kind of hybrid, but they added this tall switch or programmable switch where they current state of migration stored, and they decide where to send the request to the destination or the source. So all non-migrated requests will go to the data to the source, and migrated will go to destination. As they claiming, with no downtime, they have always a high throughput in cost for negligible extra data and client overhead. And the migration time could be adjustable depending on what you need and what's the purpose of your application. So a little bit about architecture. In architecture, we have the clients, the tall switch, the storage services, and how it works. So client sending requests to the tall switch. Tall switch decides where the requests go, to the source or destination. To track the state, they divided the groups by keys by groups, and marking them as like, are they already transferred or not? They do it with yeah, they do it with bloom filters. Basically, how it works. They have two kinds of bloom filters. One that's recording the current state, if it's ongoing operation or not in CBF. They're recording if it's migrating right now. And in normal bloom filter, they're recording if it's already migrated. They can have false positive results when it's marked as migrated already, but not out from the migration state yet. So in this case, they just sending reads to the both destination and source. So what's the key points, key size? So they have fine-grained migration state tracking is limited on switch resources. That's why they divided it into groups. The group's normal size is about like 2 to the power 20 keys in it.
So Alakbar, let's
Yeah.
pause for a second, right? So the switch, right, has
Yes.
that map of like what key has migrated and what has not, right?
Yes.
And essentially, when the client talks to a database, the switch will either send the request to the original, like the source machine,
Yes.
if it has not been migrated,
Yes.
or the destination if it has been migrated,
Yes.
right? And if the switch is not sure, then it will send the request
To
to
both.
both to try to figure out like where the data is, right?
Yes, exactly.
Okay.
So yeah, they maintain data consistency during migration with the spoon filters I just described, and they have some dynamic migration policies that could be configurable, like how much time it would take, what the size of the groups, and some other minor stuff. So how it works, was the workflow. So source server starts migration and registering the new group coming to the destination service. So when the client queries the request, it looks up in index on a switch. Is it in migrated group, or is it migrating, or is it not started migrating yet? So when migration data in group I is sent, it updates the index on a switch and replaces data on the destination server. After finishing migration of this group, it sends finish migration message that deregisters it from the current migration state and put it as already migrated, marks it that way. So afterward, cleanup happens and destination server takes over data ownership. So yeah, as I said, when it's not started yet, the group not migrated, so routing will be go to the source for both reads and writes. If it's ongoing state, the read will go to both destination and source, and the writes will go just to destination as we have in just simple hybrid method. Yeah, the same for the false positive. So since they're not sure about what's happening in the system right now, is it already migrated or not, they, to be sure, they send it to boss. And when it finishes migrating, they sending boss operation to the destination. So they their version shows that it improves query throughput by 6.5 to 416% on the different ECSB workloads. It supports diverse migration policies with different performance goals, including query throughput, latency, migration, completion time, and improves average query throughput from 32 to 78% compared to the baseline protocols. So NetMigrate can achieve above improved performance with slim BF and CBF space allocation within the switch memory limitation. Yeah, and it creates negligible bandwidth overhead since they not sending to the both source and destination all the time, but only when needed. So the test bed was Intel Tofina, 8-core CPU on an Intel Xeon with 64 gigabytes of memory. So they have several workloads. They divided key value to the 256 million keys. Each key had 4-byte and 64-byte values. 4-byte keys and 64-byte values. So the workload ratio was from 0 to 30%, and they limited the CPU usage from 100 to 40% to simulate overloadness of the system. So yeah, the evaluation parameters are size of the Bloom filters, several hash functions, 2 to the power 17 migration groups, and 2048 key value pairs in each group. So C types of migration, source-based, destination-based, hybrid. Yeah, and in their comparison, we can see that on average, the throughput in of the system is slightly higher than with baseline compared algorithms, but it has some spikes and downtime at the same time. So if in baseline algorithms it's stable, here we have like some down and up points that I don't like actually. Yeah, the same with 50% latency. On average, it's better, but on 99 percentile, it's much worse. Yeah, and here is with 40% CPU budget, the latency of the system. As you can see, it's not performing much greater than the baseline algorithms. Yeah, I think that's all for me.